Like many things in science, we classify stars because they're all different from each other. So stars are not all the same as you look out there in the night sky. If you look really closely, or even with binoculars, you can start to see different colors of stars. And if you've got a telescope, the colors really stand out and you start to see the different colors of these pinpoints of lights that we see. Well, why are they different colors? First of all, it shows how hot they are. So the hottest stars out there are that white blue, and the coolest stars out there are a dark red color. Those hot stars have a surface temperature of about 40 degrees Celsius, and the coolest ones are about 3,000 degrees Celsius. It turns out that the color of the stars is also related to their size. So the hottest stars are also usually the largest, and as they move to red stars, they become the coolest and the smallest.
You probably might not know this, but because everything has a temperature, everything emits light, like this ball. But turning off all other sources shows it doesn't seem to emit light at all. Light or electromagnetic waves are very diverse and come in all sizes or wavelengths, but our eyes are unable to see most of them. There is also something called frequency, which is the number of times the wave jiggles in a second, and multiplied by the wavelength gives the speed of the wave. The speed of light is a universal constant, which means that more the wavelength, less the frequency. Now, because of its relatively low temperature, the ball is emitting light at a wavelength called the infrared, which our eyes cannot see. But infrared light can be detected by instruments, and this is how some night vision cameras work. They detect the infrared light emitted by objects due to their temperature. Things with different temperature emit light at different wavelengths. Hot objects emit light at lower wavelength or high frequency, which means the wave is jiggling fast and has more energy. Which makes sense because hot objects should have more energy. This is also how, on heating objects, they start emitting light at a wavelength which starts to become visible to us. Our eyes, though being able to see only a narrow range, does have an awesome way to distinguish the different wavelengths which it can see. It does this through color, with red having the longest wavelength, that is the least energy, and blue having the shortest wavelength, that is the highest energy, and everything else in between. What does all this have to do with stars? Stars are hot and their temperature corresponds to wavelengths which our eyes can see. Stars come in different colors, and we now know that the blue ones are hotter and the red ones are cooler. So what's the deal with the size of stars? In 1910, two guys called Hertzsprung and Russell tried to see if the size of stars had anything to do with the color. They found that most stars follow this very neat pattern, with the blue hot stars being bigger and the red cool stars being smaller. A little more knowledge on nuclear physics tells us why this happens. Most stars in their cores are fusing hydrogen to helium, which is their main source of energy and hence the temperature. This fusing can only happen once the conditions inside are hot enough due to high pressure of the material forming the star. The bigger, more massive stars have more material and hence more pressure, and hence a bigger core which is producing more energy, leading to a higher temperature and making it bluer. The blue stars are about 10 times hotter than red stars and 100 times bigger. But don't worry, Team Red, blue doesn't get more of everything. Because blue stars use more hydrogen, they also die out faster, and there are also way fewer of them. I guess there is a plus side of being small.
Our sun is an average sized star, and its temperature is only 5,000 to 5,500 degrees Celsius. So another way that stars are different, not just in color and size, but is in their brightness. So stars range from very, very faint stars to very, very bright stars. Now, when we're standing on Earth, we're really far away from these stars. So some of the brightness depends on how far away the stars are from us. So this is what we call the magnitude of stars, and it's totally dependent on how far away we are from them. So if the magnitude is large, we're probably really far from the star. And if the magnitude is small, it's just the opposite of this faint and bright, isn't it? Then we're probably really, really close to that star, in relatively speaking. So that's not really useful. But if you were to compare it, Pluto, which is really not very bright, it's reflecting very little light, has a large magnitude all the way through Venus when it's at its brightest and a full moon, and our sun has a small magnitude from Earth because it seems so bright to us. You can kind of think of magnitudes like classes. This would be a class 1 over here at the sun, and a class 5 would be down here at Pluto. So that's not very useful. What we would rather measure is what's called luminosity, and that's actually a measure of how much energy that star is giving out. And we measure that in relative to the sun. So if a star is incredibly bright and giving off a lot of energy, perhaps it's 4 times our sun. If it's actually faint and not giving off as much energy, then maybe it's a quarter of a sun. And so we use the sun as a measuring stick. Now our sun is of course the brightest star we can see. Many, many stars would be even brighter if we were as close to them as we are to the sun. So stars are not all the same. They're different in color, which is related to their temperature, and how much energy they're giving out, which is related to their brightness, and it's also related to their size, because large stars have more mass and more pressure so that they can do more fusion, nucleosynthesis, and be emitting more energy.